Hi, hi everyone. Uh, Welcome to the Tuesday B session. Um, we have two papers in this session. We have one of these two papers, excitingly, is the best paper runner-up. So please stay tuned to see that. And then following the first two papers, we have an exciting keynote by Alla Sheffer immediately after these two presentations. So the first paper in this session is by Charles Saunders and Vivek Goyal from Boston University, and it is titled Fast Computational Periscopy in Challenging Ambient Light Conditions.
Fast computational periscopy in challenging ambient light conditions through optimized preconditioning. In computational periscopy, we have a scene of interest out of direct view of the observer. Between this scene and a visible imaging wall is an occluding object. Light emanates in every direction from the hidden scene, some of it hitting the visible imaging wall, and some of it being occluded from some parts of the camera's field of view by the object. This occlusion improves the conditioning of the inverse problem of recovering the hidden scene from a single photograph enough such that it is possible. The forward model can be written in the following way, where Y is the camera measurement, A is the light transport matrix that models radial falloff, occlusion and foreshortening effects, F is the hidden scene we wish to estimate, and B is an additional ambient light or background contribution. A certain camera field of view and occluder pair results in a computational field of view in the hidden area. That is, the area which is well conditioned enough for recovery. This is analogous to the usual field of view of a camera, i.e. where the system is capable of imaging. Light coming from a point within the computational field of view casts a unique shadow into the camera's field of view. Points outside of the computational field of view do not cast shadows into the camera field of view, and their contributions can be considered a background term, which can be included in the B term. In previous work, this inverse problem was successfully solved to reconstruct images of a hidden scene using only a single photograph of the blank relay wall as an input. However, these constructions were performed using data measured without any additional ambient background light. In realistic scenarios, scenes will be illuminated by light sources in the environment such as room lights. The light from the room lights will reflect from the hidden scene and into the camera's field of view. However, direct light from the room lighting will also reach the camera's field of view and will be much stronger due to the shorter travel distances and no additional reflections. Therefore, the uninformative background light contribution in the measurement will usually be stronger than the contribution from the hidden scene itself. Experimental reconstructions using the method from the previous work are shown here for a situation where the room lighting level was increased in order to decrease the signal to background ratio. We can see that the differencing provided some robustness to the background light, but as the signal to background ratio gets to less than 1, the reconstruction quality significantly degrades. To try to improve robustness to ambient light in the previous work, they noted that the background term varies very slowly spatially as it comprises light arriving from outside of the computational field of view, which is unoccluded. Therefore, it can be approximately cancelled by taking differences between neighboring pixels in the camera measurement. This can be achieved in practice by augmenting the problem with a finite differencing matrix. The following optimization problem was hence solved to form the reconstruction, but as we saw previously, this method fails at low SPR. However, the use of this differencing matrix does inspire a new solution. Is there a better matrix out there that we can put in its place that isn't chosen heuristically? Well, we can aim to find such a matrix that can optimally cancel any possible background contributions. We start with a function which computes the camera measurement we would get from a point light at some position alpha. We also note that any background contribution can be modeled as an integral over such point lights. We could then aim to solve a problem of this form, where we aim to find a matrix P which cancels out all possible point light contributions. However, this is intractable. Instead, we propose sampling the point light function for various alphas and stacking results as columns in a background matrix P. As the response of the point light function varies very slowly with alpha, this is a good approximation where the span of the matrix B lies very close to the span of all possible background contributions. Here we show the sampling points in blue and the camera's field of view in red, along with two example point light renderings. We can now rewrite the problem in a tractable form. We can actually take this one step further and aim to make our background cancelling matrix a preconditioner by making the product PA as close as possible to the identity. The problem now has a familiar closed form solution. We augment the light transport matrix A with additional examples of possible background contributions, take the pseudo-inverse, and discard rows that don't pertain to the hidden scene image. In practice, we actually find that this preconditioner matrix is in fact an actual pseudo-inverse of the light transport matrix. When we go ahead and compute this background cancelling matrix P, we can see that the structure we get does indeed resemble the heuristically chosen finite differencing structure from previous work. We can look to solve a similar optimization as before, but where the finite differencing matrix D has been replaced by our new background cancelling pseudo-inverse. As P is a pseudo-inverse, the optimization problem for recovery of the hidden scene simplifies to simply left multiplying the camera measurement by P and then denoising using the proximal operator of total variation. This results in a significantly faster reconstruction than when using the differencing method from previous work, which required a lengthy iterative procedure. Here we show a flowchart of the recovery. We left multiply the camera measurement by P, denoise this with the proximal operator of TV, and lastly perform adaptive medium filtering to clean up the final result. On the top row here, we show the same results as earlier, where we used the differencing method to reconstruct images using measurements with decreasing SBR. On the bottom row, we can compare this with the new method using an optimized background cancelling matrix. We see that the proposed method hardly degrades at all with decreasing SBR, and also forms reconstructions about 80 times faster. If we pre-compute the P matrix, the reconstruction speedup is around 3000 times. Here in the left column, we show the mean squared error of the differencing method compared to the proposed method evaluated over a number of different trials using experimental data that was augmented with a number of background measurements in different conditions. We see that the proposed method outperforms the differencing method at low signal-to-background ratios and performs similarly at high signal-to-background ratios. On the right, we show one example of one such trial for each of the signal-to-background ratios tested, and we see that using the optimized P results in much better reconstructions. We can see how well the proposed technique cancels background contributions by reprojecting a solution into the camera measurement space. In column A, we show a measurement with low signal-to-background ratio. Column B shows the background present in the measurement, and column C shows the signal from the hidden scene without background. In column D, we see the reconstructed camera measurement, which looks very similar to the background-free measurement. For comparison, in column E, we show the same for the differencing method, which clearly loses some of the information present in the shadows. As mentioned previously, if we pre-compute the P matrix, which is fixed for a certain scene geometry, the reconstruction we can form is about 3,000 times faster than the previous differencing method. As it is so much faster, we are able to recover videos at around 40 frames per second. Here we show a recovery at 16 frames per second, using a slightly different reconstruction algorithm that also applies total variation denoising between frames in time. In this talk, we have shown how we can formulate and solve an optimization procedure to find a preconditioning matrix that not only improves robustness to background light, but also emits faster reconstruction algorithms for passive non-line of sight imaging problems.
Okay, great video. If anyone has any questions, please, we encourage you to put them in the YouTube live chat or the chat on the YouTube live channel. I'm not seeing any right now, so I could start with a first question. So for this type of background influence, I guess, I would imagine that the dynamic range of the image sensor is relatively important. Have you explored looking at like these really super high HDR capture strategies for many bits per pixel to help assist with the ill-posedness of the problem?
Yeah, that's a really great point. So in this work, the signal background ratios we were looking at weren't low enough such that we had to worry about the dynamic range too much, at least. But yeah, if we wanted to push it further, we definitely want to either think of new algorithmic development to just deal with the fact that we have a low bit depth, or yeah, look at sort of high HDR strategies.
Okay. And I guess, yeah, just one other question is so the light source causing the background, the light causing the background is coming at a very different angle, right, than the light coming from the object, one would assume in a typical geometry. So can you exploit that somehow to assist with its removal? Is there, accounting for the albedo of the surface somehow, things like that? Is that reasonable?
Yeah, kind of. What we're hoping to do is essentially we have this like computational field of view, which is anywhere that's casting this unique shadow. And then we're defining background light as anything that isn't casting a shadow then by sort of definition. So in essence, that's kind of what we're doing. So things, out of a certain angular range and our background, and we know that they're not casting a shadow, and that's why this works. Yeah, that's kind of why it's working. I guess other things you could do that we've been thinking about that could be interesting is actually, thinking about whether like room lighting is more likely to have certain colors and things like that. Maybe you can utilize that too.
Yeah, good point. Okay, I don't see any other follow-up questions, so we'll move on to the second talk in this session. It is titled High Resolution Deep Imaging using Confocal Time of Flight Diffuse Optical Tomography. The presenters for this paper are Yangyi Zhao and Ankit Raghuram, and the co-authors are Hyun Kim, Andreas Hilscher, Jacob Robinson, and Ashok Veeraraghavan. Some of those authors are from Rice University, and others are from New York University and Columbia University. Yeah, let's watch the video now.
Hello, my name is Ankit Raghuram, and with my co-author Yangyi Zhao, we are presenting high-resolution deep imaging using confocal time-of-flight diffuse optical tomography. Optical imaging techniques have gotten more prevalent in vivo imaging tasks. Optical wavelengths are beneficial because light is able to penetrate through biological tissue, reaching regions of interest. Optical methods can be ported into small form factor instrumentation for easy use that are not harmful. And the body comes with some endogenous optical indicators, one of them being hemoglobin, which preferentially absorbs certain wavelengths of light. Using these techniques, a variety of in vivo applications are possible, like functional brain imaging and tumor detection. To be successful in these tasks, we would like millimeter scale resolution greater than 15 mm pads deep into tissue. The biggest challenge to optical techniques is light scattering. When traveling through media with particles along the same order size as the wavelength of light, light can be redirected or scattered by these particles, resulting in circuitous paths rather than straight ones. If you're using a standard lens, this will harm the scene to camera mapping, resulting in poor resolution. Ballistic imaging techniques have tried to circumvent this issue by rejecting any photons that are scattered. Optical coherence tomography, confocal microscopy, and two-photon microscopy are a few of these ballistic imaging techniques. However, as you go deeper into tissue, the number of ballistic photons falls off exponentially, limiting these techniques to less than 30 mean free paths deep into tissue, where 1 in 10 power 13 photons are ballistic. Diffuse optical tomography is a technique that makes use of the scattered light rather than rejecting it. It measures the intensity at a detector from a source. In this diagram, the red dot is the source and the blue square is the detector. This intensity carries information about the media photons interacted with. The green cloud illustrates the number of photons that pass through a particular voxel, also labeled as the sensitivity. By making many different angles of measurements, DOT can estimate the optical properties of the media, in our case absorption. Once you have these measurements, a common pipeline for reconstruction is to make a guess of the parameters, compute an estimate of the sensor measurement using a forward model and scene parameters, calculate the error in this prediction to the actual measurement, and use this error to update the parameters. The main downfalls of DOT is poor spatial resolution on the order of centimeters, and common reconstruction methods are slow, which can take seconds to minutes to converge. Time of flight DOT, or TOF dot, operates similarly to DOT, but in addition to using intensity, it also uses time of arrival distribution at tens of picosecond time bins for a particular source detector pair. This additional information better localizes where the photons are coming. As you see, the sensitivity changes as we look at different time bins. This added dimensionality leads to improvements in spatial localization and resolution, even with similar reconstruction approaches. However, with increased dimensionality, these methods take even longer to solve. Also, there needs to be sufficient integration time to get high SNR measurements. Many works aimed at addressing the issues of DOT and TOF dot, and we list a few here that gave us some inspiration for our method. Linearization of the inverse problem for DOT results in faster reconstruction time, similarly accurate results, making only a few assumptions. Structured light in DOT is aimed at taking fewer measurements to improve upon acquisition time, and confocal DOT uses time of flight and confocal measurements that contain the most information to reconstruct macroscopic targets while reducing overall acquisition time and reconstruction time. However, there still exists a need for a fast method that can obtain millimeter scale resolution 50 mean free paths deep into tissue. We proposed confocal TOF dot, or CTOF dot, that takes advantage of time of flight to get millimeter scale resolution, smart measurement selection, and a convolutional approximation for real-time reconstruction, and multiplex measurements for reduced capture time.
Now we will review the theory for the forward model. This will provide the motivation and background knowledge for understanding our proposed approach. We use a multi-layer model to represent our scene. Each layer possesses homogeneous optical properties. This model can be targeted to different applications. For example, in neuroimaging, we could represent the skull, CSF, and brain layers of the human head. For imaging through skin tissue, the layers could represent epidermis, dermis, and so on. We assume the target features are embedded in this lab. The imaging targets are the spatial distribution of optical perturbations, known as mu. We will primarily focus on optical absorbers as the perturbations, since many biological features of interest, including tumors and functional activity in the brain, can be detected by measuring changes in optical absorption. To probe these features, we consider an array of sources and detectors, M. We wish to establish a relationship between the set of optical parameters mu and the measurements M. This is done using the sensitivity. The sensitivity tells us for each location if there is a perturbation, that is, a small change in the absorption, how would this affect the measurements? Using the sensitivity, we can approximate the forward model as a linear system, which is a reasonable approximation in many practical situations. Now, after using this linear approximation, we can discretize our scene and vectorize the associated equations. Finally, our forward model can be expressed in the following matrix vector product: M equals J mu, where mu is our scene, M is our measurements, and J is the sensitivity, generally known as the Jacobian matrix. One challenge of using this approach is that the Jacobian quickly grows intractably large, reducing the memory efficiency and increasing the runtime of the reconstruction algorithms. This is because the number of elements in Jacobian is equal to the product of the number of sources, detectors, time bins, and voxels. And so we will outline how our approach, incorporating confocal scanning and multiplexing, can address this challenge. To reduce the number of elements, we use a confocal geometry. This has an immediate impact since the number of rows in the Jacobian is now proportional to the number of detectors, rather than the product of the number of sources and detectors. We can also apply a convolutional approximation rather than a full matrix vector product. We consider a k by k source detector array, as seen with k by k voxels and nt time bins. For the linear model, the computational complexity is k to the 4th times nt, whereas using a convolutional approximation, this becomes k squared log k times nt. To show that this convolutional approximation is valid, we want to demonstrate that the Jacobian is topless. We do this by visualizing the rows of the Jacobian. Each row corresponds to the sensitivity profile for a particular source detector pair. For each row, we see roughly the same sensitivity profile with a spatial shift corresponding to the position of the source detector pair. In addition to improving the algorithm runtime, we also want to reduce the measurement acquisition time, which is another bottleneck. To do this, we will use source multiplexing. In our approach, the main benefit of CTOF comes from the decrease in illumination intensity as the source detector separation increases. This implies that the signal measured by each detector will primarily come from the adjacent source. This allows for parallel acquisition with source multiplexing. For this image on the left, we have a source placed at the center of the image, and we see that the light intensity falls off as you move further away. Here on the right is a visualization of a 4x4 source detector array. We show different illumination patterns. We have overlaid the illumination falloff for sources that are turned on. We see this effect that the strongest illumination is at the adjacent detector, allowing for parallel acquisition. Now that we've gone over our approach, we next want to show some of our results. We start with a performance characterization that we carried out in simulation. Here we show a resolution test. Our scene is 2 lines of 0.5 millimeter thickness separated by 0.5 millimeters. We see in the top row, without time domain information, we record a noisy measurement, and we're unable to resolve the 2 lines. Whereas using CTOF in the bottom row, we obtain cleaner measurements and resolve these 2 lines. Here, we benefit from using time gating and information from multiple time bins. We also want to compare the conditioning of the Jacobian matrices for DOT, TOF, and our approach of CTOF. For DOT and TOF, we consider a 5x5 source detector array, which is 625 total measurements. With CTOF, we consider a 25x25 source detector array. Since we only consider the collocated source detector pair, this also corresponds to 625 total measurements. We have plotted the singular values on the right. We see that CTOF has a much slower decay in the singular values, indicating a better conditioned matrix. Finally, we also want to show the improvements in the algorithm runtime. We compare the runtime for the reconstruction algorithms using DOT, TOF, and CTOF. We test how this runtime changes as we vary different parameters. On the left, we show the runtime versus the source detector array dimensions. And on the right, we show the runtime versus the number of voxels discretizing our scene. CTOF achieves approximately an order of magnitude improvement over DOT and about 2 orders of magnitude improvement over TOF.
We next want to test how our method performed in real experiments. Here we show a rendering and a picture of our experimental setup. We use an e-ink display to display absorptive targets to image through the scattering media. We emulated an array of sources and detectors by scanning a single pixel SPAD and laser source using galvos onto the sample as shown in the zoom in. The first experiment we conducted was corroborating the spatial resolution of our system in experiments. We scanned the laser and detector across the indicated region shown to the left. Our target was 2 absorbing lines. In each case, the spacing and line thickness were equal. Shown to the right are CTOF 1D reconstructions, showing our method is capable of imaging 2 lines at 0.5 millimeter separation or 1 millimeter center to center distance. Next, we wanted to show the benefit of multiplexing had on acquisition time. Shown on the left are plots indicating the PSNR of an image reconstruction through scattering media with different integration times. You can see with multiplexing, the PSNR is improved at smaller integration times and thus smaller acquisition times, demonstrating the benefit multiplexing measurements versus scanning them individually. On the right are corresponding image reconstructions at different integration times. For standard absorption reconstruction, we can achieve comparable image results to TOF through a thick skull phantom. However, we see that there's a 2 order of magnitude improvement in reconstruction time and a 1 order of magnitude reduction in acquisition time due to the number of scanned points. We also demonstrated our approach is capable of imaging fluorescent targets through scattering media. The raw measurements shown in the second column gate out the main excitation peak, resulting in a measurement containing mainly the signal from the fluorescent target, which can then be reconstructed. We can see the effect of not gating out the excitation light in the 2 images to the right. The measurements are dominated by the excitation light, and the reconstruction cannot resolve the oval-line target. And finally, we demonstrate experimental 3D results using CTOF dot. The ground truth and 3D reconstruction can be seen to the left. On the right, we show Z slices for the ground truth, reconstruction, and thresholded reconstruction. At different depths, we are able to resolve the pillars that range between 3 and 7 millimeters deep. To summarize, we developed CTOF dot, a method that provides high-resolution, deep imaging into scattering tissue. It is capable of millimeter resolution with sub-second reconstruction times, and with the help of multiplexing can reduce acquisition time. We have shown CTOF dot perform in simulation and experiments using both 2D and 3D geometries. We hope CTOF dot can bridge the gap between ballistic techniques and traditional DOT approaches by providing high-resolution, deep imaging. This work was funded by DARPA as a part of the Moana project, whose goal is to perform minimally invasive brain-to-brain communication. CTOF dot is one approach we can use to perform neural reading non-invasively. Thank you.
Okay, great. Nice video. Any questions? Again, please feel free to share them in the YouTube live chat. We have one that just popped up. Great. So it says, great work. Could you comment on how photon noise affects your reconstruction?
Yeah, definitely. So photon noise is, so we just model having Poisson noise in our simulations, and we experience it in our experimentally capturing measurements as well. Of course, if we have a significantly reduced exposure duration, then we'll be really dominated by Poisson noise, which will make image reconstructions a bit more difficult. But with a sufficiently long exposure duration, we found that we could get pretty good image reconstruction quality.
Got it. A second question. Also, great talk. How much sensor time sensitivity do you need for your application? I'm not fully sure what sensor time sensitivity means, but maybe perhaps you know, Vivek, maybe you can.
So at least for each scan, usually we're taking about 100 millisecond captures. So scanning through all the points takes seconds to obtain the measurement. But again, with we're hopefully modeling this scanning system, hopefully will be able to be converted to an array, and with an array you can have faster acquisition times.
Got it. Yeah, I guess that was going to be my question. How might geometrically or otherwise you transition this to, let's say, a SPAD array type measurement system as opposed to a single SPAD?
Yeah, so the hope would be to essentially have a full array embedded with both the time of flight, so SPADs, and as well as on-chip light sources, so VCSELs most likely embedded together. And then hopefully with this type of a prototyping system, we can see what are the most optimal configurations of the light source and detector geometry that we can use.
Got it. Okay, one last quick question. Is there a theoretical understanding of minimum size you can resolve given a set of tissue parameters? Is it dependent on the camera/light itself?
Definitely. So it's dependent on definitely several parameters. So different camera parameters, the timing resolution, as well as the thickness and the amount of scattering we're trying to image through is, of course, also very significant. We showed that for a biologically relevant sample, so corresponding to both the optical thickness, the physical thickness, and the scattering properties of human skull, we could achieve around millimeter to even sub-millimeter scale resolution. So, but of course, across different biological samples, there's going to be, of course, varying properties. So we would need to account for those different cases.
Okay, great. I think we'll wrap it up there. Please stick around for the keynote session. It's going to start just in a few minutes at 12:30. So please stay tuned. Okay, hi everyone. Welcome back to the keynote session for today, which will be presented by Dr. Alla Sheffer. The title of Dr. Sheffer's talk is Parsing and Processing Artist-Drawn Imagery. So just a brief introduction to the speaker, the keynote speaker. Dr. Alla Sheffer received her PhD from Hebrew University and is currently a full professor at the University of British Columbia in Canada, where she investigates algorithms for shape modeling and analysis in the context of computer graphics applications. Dr. Sheffer has co-authored over 100 peer-reviewed publications. She is the recipient of the Canadian Human Computer Communications Society Achievement Award, a UBC Killam Researcher Award, is a fellow of the Royal Society of Canada, a fellow of ICCP, and a member of the SIGGRAPH Academy. And she has also served as associate editor for all three major computer graphics journals. That's ACM, Transactions on Graphics, IEEE, Transactions on Visualization, Computer Graphics, and Eurographics, Computer Graphics Forum. So we look forward to her really exciting keynote talk and are happy to have her here. So with that, please take it away, Dr. Sheffer.
Thank you, Rourke. Let's hope the technology cooperates and everything works. Okay. So, see. Okay, it did not cooperate. Now it did. Okay, so as mentioned, my goal today is to talk about parsing and processing artist-drawn imagery, which is a somewhat different topic from what most presentations at ICCP are about, because, well, usually when people talk about image processing, what you talk about is natural image processing. So tasks such as, for instance, changing image properties or going from 2D images to 3D data. And so we talk about real data, as in stuff that's actually captured in the wild. And if you think about algorithmic goals, you'll be thinking about things like realism, as in how real do things look and how correct they are. When we talk about artist-drawn image data, what we talk about is data which is man-made or human-made, and the goals are going to be very different because we are no longer talking about realism, because we're talking about artistic outputs and therefore artistic inputs and artistic outputs. We no longer have really a notion of correctness because there is no ground truth data behind what we are working on necessarily. So there is kind of the question mark next to correctness because we need to understand what we will even mean by correctness. Like, what is this 3D object that this image is conveying? Probably this is what you had in mind, but why? What does it actually mean? So when we talk about goals of artist-drawn image processing, really what we are looking for is consistency with viewer expectations. There are no objective metrics. The metrics we're interested in are purely perceptual. And what does that mean? Well, here are some tasks. Here is a raster image, here is a zoom on that image. And we may want to vectorize it, so represent it in a continuous form. And probably everybody in the audience can, in your head, imagine what we want the output to be. But if you think about why, that's where you start going into like, why is my brain thinking a certain way? And that's where the problems of processing of artist-drawn data come up, as in, what do we want? What's our metric of success? Or another example, when artists draw freehand, this is kind of a typical drawing that they create. Now, if I were to ask you, what are the meaningful curves in this drawing? Like, what's the shape? Well, probably what you will see is this. And again, with the question to ask is, okay, how do people go from here to here? And how do we then algorithmically replicate this process? So this is kind of at the heart of processing of artist-drawn images, this question of what do viewers perceive and how do we try algorithmically to capture that? So what we kind of have here is this funny problem, because we know what to expect. Humans, when shown artist-drawn data, usually have pretty strong opinions about what the expected output of a processing operation is. But if we think about how do we express it, we don't have an immediate equation in our head, as in, here is what we want. We don't really know how to express it. Therefore, when we talk about processing of artist-generated images, the first and probably hardest task, I would argue, is to formulate human expectation. Like, what do we mean by getting the goal that we want? And then we still need to solve it, which is still hard. But in my talk today, I'll really look at kind of this first part, because once we know what function we want to minimize, we know how to minimize those things. It's the figuring out what do we want to minimize. And really what we want is we want to learn the human perception of that imagery. The question is how? And what I'm going to talk about today is some somewhat representative examples using different tools, and then maybe try to highlight common threads among those. So here is one possible approach. This is a work I was a co-author on, which was at SIGGRAPH Asia 2018. And the question that was asked is, okay, here we have a 2D sketch. How do we get a 3D model out of it? And you can kind of imagine what you wanted to get out of it. And the approach we took was, well, learning, right? If we want to try and solve a task of going from a sketch to a 3D model, we want learning data. And the approach in that paper was, well, we can take the inverse task. We know how to create NPR renders given 3D models. So we can train an algorithm to do the opposite task. And you design your lovely network, and I'm not going to go into the details, and you can get something reasonably nice. So here is your 2D, here is your 3D. I don't know what your opinion about it is. It's reasonable. The problem, it's synthetic data, right? The data used for this algorithm is NPR renders. The good thing about NPR renders, there's a lot of them. We know how to generate them, right? Rendering is a task we know how to do. The problem, well, these are sketches used in that paper. Human beings don't draw like that. Let me tell you that. If I were to ask you to draw a human body, you would not use this type of drawing. So yes, it's an NPR style drawing, and you can train on that type of data, but people don't draw like this. You can train the users, which is what we did in this paper, as in we taught them a little bit about how to draw, and they can then do that, but that's far from ideal, right? When we want to look at artist data, we want the artist to draw as naturally as possible. We don't want to train them. So what we want is to learn what humans want. And that means learning from humans, not from algorithms, because humans are not algorithms. So this is a valid approach, and in many cases, it can help you a lot progressing with research. But I strongly believe that we really want, when we want to learn how to process artist data, we want to learn from artists. As in, the ultimate goal should be for users to draw stuff the way they want to do it, not the way we force them to. So the goal can be thought about as 2D to 3D in the wild, as in we want to get real 2D drawings and we want to get 3D. So at the high level, the goal is exactly as I kind of said, is we want to understand how people draw, and we want to understand how people perceive drawings and formulate this kind of knowledge as some kind of objective and constraints. Right? So we kind of be able to draw, look at the drawing, understand how and why an artist decided to draw it that way, and how and why observers perceive it that way. And really, we want to look at we can think about it as a two-stage process, because real drawings are messy. Real drawings do not consist of nice, clean lines. And we can think about the process of going from sort of messy drawing to clean drawing to 3D model. And let me talk a bit about this, going from a messy drawing to a clean drawing. How do we solve this problem we have seen earlier of going from this owl to the one on the right? And at the core of it, if you think about, there are two steps. First one is identifying which strokes in the original drawing belong together or depict a single common curve in what the artist intended and in what the viewers see. And then once we have this grouping, we can think about fitting a curve to that group. And inherently, both steps have challenges. And we have, but I'm not going to talk about it today, a paper which will show up at SIGGRAPH 21, which goes from this grouping to the curves. What I will talk a bit about more here is going from the drawing to the groups. And again, it's an interesting question. Ask yourself why you mentally group the curves on this drawing the way you do. Or in this case, here's kind of a subset of a drawing, which is totally abstract. There is no content here. This is not about recognition. This is about mental grouping. How many groups of strokes do you see here or here or here? Just do the mental exercise. My guess, this is how you group the strokes. Now try to think why. What properties of human perception of drawings, of familiarity with how other people draw, got you to this point? And let's look at this drawing here again, and let's look at some clusters of strokes which people perceive as single curves in this example, and try and see what makes us group them. And there are several cues which come from perception literature and Gestalt psychology literature. And those basically tell us that usually we group strokes if they're roughly parallel, if they are close to one another, where closeness is not absolute. The distance here is the same as the distance between the other pairs of strokes over here. Like this distance here and this one are essentially the same. What different is the density. So you perceive things as belonging together if their density is roughly even and the gap between them and others is much further. So there's kind of this notion of density which leads to, which facilitates mental grouping. And this is the idea inherently that inner cluster distances are much smaller than inter-cluster distances. So if by analyzing perception literature and analyzing design tutorials, we can come up with a criteria for what makes people group strokes with it. We want to look at roughly parallel strokes, which are forming narrow groups. So something like this has even distance, but the result is not a curve, right? We can see this, we perceive this as a group rather than something like this, which we perceive as a curve, because the ratio of length to width here is much smaller than here. So we can come up with this rough definition, which is a cluster is a distinct and narrow cluster of locally parallel, roughly evenly spaced strokes. Now, this is kind of generically helpful. But the devil is going to be in the details. And how do we go from this definition to an algorithm? And in the paper in 2018, we used a two-stage approach, where we first looked at average compatibility, looking at strokes, are they kind of close enough and parallel enough on average? And then we looked at fine level analysis. So at the average level, for instance, you kept this group of strokes together, and then at the fine level, you separated them. And then you can do the fitting step and get your output. So there's a tiny little bit here. We said that things need to be parallel. How do we measure parallelism? At what angle do things become parallel? What does it mean to be relatively proximate? What does it mean to be narrow, right? Those are all kind of nice and fuzzy words. How do we address them? Well, for angle, perception literature have done that analysis, and we can use that. For proximity and narrowness, we used human perception studies, where we asked a whole range of people using different types of questions, simplified questions, which aimed to assess relative proximity. For instance, if you have 3 strokes here, at which point, based on the distance here versus the distance here, do you see them as 2 separate groups versus 1 group? Or for narrowness, at what point do you still see something as a line versus a rectangle? So what this gives you is kind of a principled threshold setting. Okay, so this is how you can type and approach this perception questions and quantify and go from here are perceptual cues, they're kind of general, to how do we actually apply them in real life in an algorithm setting. Now, as I said, that was just the first step, going from a messy drawing to a clean one. How do we go from a clean drawing to 3D? And this is an early work, this is 2012, and I'll talk about several kind of iterations of this research. And probably everybody here can imagine a 3D object drawn from this 2D drawing. Now, probably you can start thinking about how, because this is not about recognition, right? I mean, it's not like we see duffel bags every day. Well, maybe we do, but this, we're not, why are we seeing the geometry of this particular duffel bag in a particular way? And what we did in 2012 is we focused on, let's call it shape from shading equivalent, or in our case, shape from drawing. So what we looked at is an extraction of normals from images. So not necessarily full-blown 3D depths, but normals. Once you have normals, you can do cool things like nice shading and lighting. And the question becomes, why do people see this as 3D? What kind of cues are they using? And the curves here are not random curves. Those curves highlighted in orange are what's known as cross-section curves. And it's a type of curve that artists use a lot. Here are cross-sections on another drawing. And those curves have very clear properties, which you can look at if you look at design literature and books which teach artists how to draw. It's not an accident that artists know how to convey 3D shape effectively. And when you look at that literature, what it suggests is that when people draw cross sections, they draw curves which are planar, which are orthogonal, both at the tangent level of the curves and at the plane level of the planes which those curves are in. They preferentiate symmetric curves, so ones which are geodesic, and they prefer views which impose minimal foreshortening. Because the idea is that the length of the curve in 2D is not insanely off compared to its length in 2D. Now, of course, that's slightly fuzzy, but once we try to formulate those, we can indeed arrive to a constraint minimization problem, which tells us how to get those curves from the 2D drawings. And we can use that information to compute normals and then do all kinds of cool shading effects. So is that it? Are we done? Well, not really, because this assumes that we have inputs which are very clean and which are clearly annotated. The colors here indicate that the user actually colorized every curve based on what type of geometric entity that curve is. Data in the wild does not have that annotation. Curves in the wild are also not all of a symmetry curves, like this one is not. It's not necessarily planar. So in the wild, not everything is clear cut. How do we go about handling that? So take two was SIGGRAPH 14. So we did not yet try to reconstruct something directly from this, but we went one step further from the previous paper and said, okay, here is a curve network. It's a lot more complicated than the previous scenario. It has occlusions and it has curves which are not just cross sections. Now we can get from there to a 3D object, like this. How do we get there? Well, we have annotation-free inputs, and we relect the assumptions. One of the things we account for, which is critical, is inaccuracies. Human drawings are never accurate. When you take a photograph, you have an accurate representation of real life. Maybe all you need to know is the parameters of your camera. When people draw, that's never the case. An artist is never going to create perfect perspective. We have studies on that. Your perspective is always going to be distorted. When an artist aims to draw two parallel lines, they'll never be exactly parallel. When an artist draws two lines which in 3D are supposed to be orthogonal, there is no exact perspective transformation which will make them orthogonal. Drawings are never exact, and regularities are selective. Some curves may be orthogonal, some may not be. Some curves may be planar, others are not. So we need to handle all of those ambiguities. And the core ideas behind that work were that in general, we have two factors. One is what I would refer to as fidelity, and its idea that 2D curves do represent 3D. They are not perfectly accurate, but they do give us two important things. 2D curves are roughly projected 3D curves. And second, this is not something people expect. Presumably everybody here looked at that image on the right here, and let me get back if my video cooperates. And if I were to tell you that this is a projection, this is not what you would have expected that projection to be of, even though it's perfectly valid, right? You looked at that drawing. If I tell you it's a projection, you imagine something in your head. You did not imagine the shape I just showed. Why? Because people really assume that the shape in 2D is somewhat close to the shape in 3D. In early computer vision, this was known as the non-accidental view assumption. And yes, artists try very hard to not select accidental views. When artists want to communicate a shape from you, they communicate it in a view where you can see the interesting stuff. And that's a very important observation, that there should be, artists do not expect you to be surprised. They want you to understand the shape. So this is probably what you had in mind. And if an artist chose that view, that's probably what they had in mind as well, because otherwise they would have chosen a different view. Sorry, my thing here just got delayed. So we can go and use that to get 3D. I think I just skipped this slide here. Open this slide here. Sorry. So what we can go now and use these observations of minimal variation combined with selective regularities and solve for the 3D shape where the regularities which we expect to happen, such as symmetry or orthogonality or geodesicity, are binary variables that you're going to be solving for and using to get the geometry. And then you can go ahead and get geometries like this one, which is probably pretty consistent with what you expected given those drawings. Now, this is still making very large assumptions on the data. It assumes that we know the connectivity, we know which curves are occluding other curves versus which ones are intersecting, and we assume that the drawing is really clean. Last year, we made kind of a first attempt at trying to go directly at processing artist drawings with all the messiness inherent to those drawings. So this is just a rough drawing drawn by an artist in a vector format environment, nothing else. There is no other information. And the goal here, as you can see, this is you go from the model to novel viewpoints of that object. And so what we have done is we have asked, okay, why do artists draw the way they do? And can we leverage the same kind of techniques that the artist uses when they draw in order to recover 3D? And the key thing we leverage here is the scaffold. When artists draw, when designers draw, they use a lot of supporting lines because it's very hard to draw 3D shapes. So what artists do is they help themselves. These are 3 stages of drawing this object. Artists start with core scaffolds and then refine it, and then they go and add details. And when you look at scaffolds, you can observe several very important things. First, you have lots of straight lines in those drawings. And many of those straight lines are axis aligned. And that helps the artists to anchor their drawings. It can also help our algorithms to parse those drawings. So you can look at axis aligned lines, straight but non-axis aligned, and then we can look at curves. And the order of drawing goes really kind of very much from along down this list. There's a mixing, but when artists draw, they anchor their strokes onto existing scaffolds. So when you add a new line, you typically add it such that it has at least one, if not more, intersections with previously drawn lines. So you have this anchoring process which the artist employs, and we, as people who develop algorithms for parsing drawings, can similarly leverage. So at the key core of our algorithm is the observation that if we have straight line drawings with known connectivity and knowing which of the strokes are axis aligned, and many of the strokes are going to be axis aligned, then we can extract the 3D geometry from this data. So if the connectivity is known and the actual alignment is known, we can compute the geometry. The big challenge is that when we have a drawing like this, we don't a priori know what is and isn't an actual intersection. Like, we don't know whether this 2D intersection is really an intersection or an occlusion, or whether this one is an intersection or an occlusion. We also have messy data as an overdrawing, which is something which again is prevalent in human drawings. People are very often draws the same intended line using more than one stroke. But our big core challenge is really to detect this 3D connectivity, figure out that this is a single intersection, and this is a single intersection, and this is not an intersection, and this is not an intersection. So how do we go about it? So I already mentioned some of the cues that people use. Axis alignment. Artists draw a lot of axis aligned lines, and we argue that observers also prefer to interpret lines absent any other information as axis aligned unless contradicted by other cues. We also note a common phenomenon when people draw, and you can kind of think about yourself also if you ever did any drawing of complex shapes, they use outside-in drawing process. So you kind of commonly start from drawing a bounding box of an object and then adding details inward. And that helps in analyzing. I already mentioned anchoring, and that's the idea that as you draw a new line, it typically is not floating in space. Typically, every new stroke you add is going to have an actual 3D intersection and maybe multiple intersections with the curves you already drew. Minimal foreshortening, I already mentioned that one, and that's the idea that in general, artists choose views where 2D lengths are reasonably correlated to 3D lengths. And a very important one, extent. Artists draw lines which extend past their last intersections, but those extensions are typically fairly small. Typically, we do not draw a line which just ends up nowhere. If we are depicting 3D geometry, typically any line you draw will have intersections close to both of its ends. How do we use those cues? Well, we follow the drawing order and we use an incremental reconstruction algorithm. So let's say this is your current sketch, and you're trying to figure out whether this is an intersection and maybe is this an intersection, right? You can have two interpretations or maybe even three. You can say my curve has an intersection at A and an intersection at B and none at C. Or maybe it has intersections to here, none here, right? So those two are intersections and this isn't. Or maybe those two are intersections and this one isn't. And well, now think back to the cues that I have just listed. And you'll see that this one is probably the most plausible one, partly because of extent and this idea that yes, intersections are more likely to happen at the ends, partly because it's already those strokes are coplanar. So there are strong cues here, which will argue for this interpretation. And you can therefore make a hard cut decision saying, yes, this is what this should be, not those two. There are other cases where this is a lot more ambiguous. Like this stroke here, is it a vertical stroke, which is just having an intersection here, and then it's just dangling? Or is it a stroke connecting A and B? Or is it a stroke which is at B and then going vertically down? All three are possible solutions, right? Do we have a strong opinion? Do you have a strong opinion? Which of those is right? Well, our algorithm doesn't. We say, hey, this is ambiguous, but maybe if we see more strokes, the answer will become more obvious. And in this case, it does. Now we have this stroke at it, and all of a sudden, this solution is much more regular, because now you have all the cues kind of happily pointing to this case, while these ones satisfy very few of the cues. So the core idea in the work is you can go follow the human drawing scheme, and you can make some decisions very early because they're very obvious. And I think it's over 70% of cases we can make those decisions early because they really are very obvious. And then in a small percentage of cases, you continue and have multiple interpretations and resolve them as more and more strokes become available. And it works pretty well. Here are some things you can do with your data once you have finished the processing. You can go and rotate your sketches, or you can treat your sketches in actual 3D objects and stretch them in 3D space. Are we done? Not yet. So here is a drawing, here's an alternative view. You may notice that all the stuff in black here, we had participants in our user study said, yes, this is perfectly reconstructed. These ones here, they shouldn't have been where they are. So it is a first step, but it's still, the problem is not solved. I think there's a lot more interesting work to be done there. The challenge inherently here is if you kind of take a step and think, why is this hard? It's very easy to access when the result is wrong. As humans, we look at this thing and we immediately go, yuck, that's horrible. We don't want that. That's evil. It's not that we have kind of a fuzzy, it's kind of wrongish, but it's almost there. We have almost a visceral reaction, like, no, this is just blatantly wrong. So it's very hard to satisfy the users because they have strong opinions. At the same time, it is very hard to create ground truth data. So yes, it's human input, and yes, people have very strong opinions, but learning from those opinions is very hard because having people annotate a drawing like that, we have tried, it takes hours. So collecting ground truth data, if you were a learning type person and said, hey, let me just get ground truth data and use my favorite learning algorithm. The problem is generating that ground truth data is incredibly hard. So let me talk a bit about a slightly different flavor of problem. Again, going back to what do humans want? And let me talk about clip art vectorization. So clip art is those lovely pictures like the UBC icon you hopefully see here, where you have very clear regions of more or less uniform color combined together. And as a human, we immediately know what we want from those drawings. We have a very strong opinion how a vector version of this icon here, of this raster image here should look like. How do we get algorithms to do it? How do we go from this raster to this vector? And the key thing is, again, our success is measured as consistency with human expectations. Here is an input. Here are a bunch of outputs. Which one of those is the right one? Or are there multiple? Well, I would argue that probably most people in the audience thought, hey, this is the one and only correct output. This is the one from our 18 paper. This is a bunch of other alternatives. And yes, people have very strong opinions about what is the right output. So as a goal of an algorithm is to match those opinions. Now, hey, we're image people. How about we learn what's right from data? What kind of data? Well, kind of obvious. Pairs of raster and vector images, right? Let's try and learn what's the right vector. Well, what kind of vector and raster? A very simple answer could be, well, why don't we take vector images and rasterize them? Well, here is a rasterization of a vector image. What's the vector image that this corresponds to in your head? Well, is this what you would have expected to get when you saw this raster? Probably not, because when we rasterize, we lose information, right? The famous Nyquist theorem, we are going to lose signal. But where the challenge is for us, when humans see this signal here, they do not expect to obtain data that was already lost. We do not, if I were to show you this as a vectorization output for this input, you would be a very unhappy camper. So no, this is not a suitable data. It really is not useful because this is not what people do. People do not invert rasterization because rasterization is inherently lossy. We do not invert it in our heads. We actually imagine something different. An alternative, well, how about we have artist-generated vectorizations? We could do that. Here is a raster. Here's an artist-generated vector. It took the artist about 45 minutes on this particular input. If I want 1,000 inputs, well, 1,000 hours is not in the budget of most of us. So how do we go about it? So the core idea in our work, in both papers that I mentioned, is to use a combination of easy to provide and non-expert human input with perception priors. So the idea being, we want to have humans provide some data, but we want them to provide data which they can provide quickly and which does not require expertise. Vectorizing something is an expert-heavy task. We want people to provide input which is easy. So the challenge is minimize the human input by leveraging perception priors. What perception priors? Well, what do we know? We know that people expect accuracy. We do expect something where if I then go and rasterize this, I'll get something fairly close to the original raster I started from. The accuracy is a strong perceptual cue. We expect what's known as simplicity. Humans expect shapes to be simple. So we really like orthogonal lines. We like straight lines. So this is not simple. This is much more sophisticated. This is much more wavy. It's a much higher complexity shape. Humans prefer simple shapes. At the same time, we also know that humans' perception prefers continuous shape. So we prefer this over this one. You might have already noticed that those cues start to conflict. Lastly, we prefer regular. So given this object, if the raster is symmetric, by God, we want the vector to be symmetric. Now, those are all cues. How do we combine them? Well, here are two raster inputs. Here are just the magnifications of the same rasters. I'm assuming everybody here has an opinion about which of those alternative interpretations you would like to get as a vector. Let's see. I'm guessing you would prefer this for the circle, for this input, and this for this one. Notice, however, that these two are actually more accurate than these two, right? This is a perfect reconstruction of this raster. This is deviating from it. Here, this one is deviating, this is perfect. Here, this is at the same time, though, more continuous than this, and this is more continuous. But somehow, as humans, we prefer this kind of mix. How do we balance those cues? So this is where we take the perception cues and combine them with learned human inputs, as in learning the balance between the cues. In 2018, the way we approached this was to split the problem of vectorization into one of detecting corners or discontinuities and then of fitting. And the corners, in order to understand where to put corners, we learned from manual annotations. That works reasonably well, but it's still pretty computation expensive, as in annotating corners still takes a lot of time. And last year, we proposed a different hybrid approach, and where what we did was we broke the problem into two steps. One was, instead of going directly from the raster to a nice piece with smooth shape, we went first to a polygon, and then we did fitting. And the reason we did it is this step, in fact, can be done effectively without any learning, as in we can directly use perceptual cues to cast the problem of polygon fitting as computation of a shorter cycle, and we can compute it pretty effectively. Then we can go from a polygon to a fit. And the way we go from it is we can really cast the problem of learning the fit as one of looking at every individual corner in a polygon and fitting it using one of three possible options. Saying, okay, this corner is exactly a C0 corner, or this corner, in fact, is fitted as a nice single smooth curve, or this corner is fitted as a smooth curve in a straight line. So literally, this becomes now a classification problem. We know how to solve classification problems. And what's interesting for us is we learn this mapping. We use a very small set of features in order to classify those mappings. So literally, we have here exactly 10 features, and we can have a minimal training set. And the reason we can get away with a training set, 23 inputs, is 23 drawings contain lots of different polygon corners. So you annotated only 23 inputs, which is nothing, but you have already got a really large number of combinations of all possible corner behaviors, and you can use those to get your outputs. So here is a visual validation. This is our output. This is the input, sorry. This is Challenger 03, which in our opinion is probably the best commercial algorithm method out there. It performs way better than Adobe Illustrator and other commercial tools. This is our 2018 method, and this is our output this year. And well, it looks right, but of course, as anybody who deals with visuals knows, we need human validation. So in our validation perceptual studies, humans observers preferred our current method over all alternatives by large numbers. So take-home message from my talk. If you want to look at processing artist-drawn imagery, you really want to look at different measures of success than when looking at natural images, because success is measured as alignment with human expectations. There is no correctness metric. There is no realism metric. It's all about, does the viewer agree with you or not. Something which is very important in this space: do not reinvent the wheel. Perception research had dealt with how to understand human drawings for about 100 years. Psychologists know what they're doing. It's very useful to look at what they know. It's also very useful to look at what artists know. People who create drawings, artists, learn how to draw effectively. So by looking at the choices they make, you can very often mimic those choices when you're doing the interpretations, and it's very useful. We want to use data. Data is extremely important, and data can be observational quantitative studies, as in specifically trying to learn from human data, from targeted perceptual studies, the metrics you are interested in. And yes, machine learning can play a role, but we need reliable ground truth data. And reliable ground truth data is usually very hard to assemble because we cannot generate it synthetically. We really need artist-drawn data to work on. We will need real content, which means it's going to be sparse because collecting real data, which is reliable, is expensive. And very often the data is not direct, as in rather than, for instance, learning vectorizations directly from raster, which is very expensive, we can often reduce that problem, as in our case, to learning, for instance, annotation of polygon corners, which is much easier to collect and can be leveraged effectively. Thank you for your attention.
Okay, great. Thanks, Dr. Sheffer, for the really wonderful presentation. Very interesting. So I would encourage the audience here to please share some questions about this keynote talk. So one question that is in the YouTube live chat is first, wonderful talk. And then it says, some of the 2D drawings could be ambiguous. For example, the cube could be inside out. Is there a systematic way to resolve such situations?
Yes. So it's interesting. Yes, there is ambiguity. That's where perception research becomes very useful, and perception studies. One of the things that we know in general, people's interpretation is people prefer things, convex interpretations over concave, and prefer the assumption of a view from above when looking at 3D shapes. So for instance, exactly, if you look at this corner here, you can interpret it as interpreted in this shading, where we are looking at the bug from above, and this wing here is convex. You can actually, though most of us, it will take a conscious effort, interpret this as a concave object. So in our work, we go with the majority assumption. It's actually interesting, when I do live talks, I usually have people do a show of hands on examples like that, and usually you have a roughly 3/4, 1/4 split in the audience, of 3/4 of the people interpreting things as convex view from above, and 1/4 insisting on concave view from below, which you can actually try and do, but for many of us, it requires a mental effort. So yes, you want to account for that. We go with a majority, and kind of with the assumption that artists target the majority in their drawings, which might not always be correct. As in, usually when you look at artists, they go very hard to try and disambiguate. So you can create ambiguous data, but typically when it's artist created, they add enough hints in to remove ambiguity.
Great, thanks. Second question from the audience. Can unsupervised learning techniques be useful for tasks such as vectorizing pixelated images?
So how do you take human perception into account. I mean, unsupervised means your algorithm learns from itself. But if your algorithm doesn't know what's a measure of success, right? Again, unsupervised learning is extremely useful if you have a measure of success, right? Let's say, hey, I'm learning human walk. My measure of success is my character managed to stay up walking rather than fall down. Unsupervised learning is wonderful because you know exactly your goal. If in our case, we don't know what success is, well, then you have a problem, right? You need to understand how to measure success.
Okay, great. Okay, third question. Is it possible to exploit CAD software that can convert sketches to 3D, for example, to constrain the solutions?
CAD software still cannot convert sketches to 3D. I mean, you draw in it. You have drawing software, you have very constrained CAD softwares which let you do certain tasks, but no, if CAD software could do that, as in if you could go from, a human drawing, I'm sorry, I'm going back here through the slides. Maybe I should have done it. Sorry, I guess, let me just go back. The ultimate goal, in fact, of something like this is to be able to replace CAD software by drawing. CAD software cannot do this task. If it could, we would be out of business. So, yeah. What you can do is you can maybe leverage the existence of CAD models to learn something about how people draw, but even then, it's not exactly clear how.
Okay, great. All right, and so that's all from the audience questions in the live chat. I just had one question. These kind of principal threshold settings you mentioned, from these earlier perception studies to, establish like, is that a line or is that a rectangle, seem to be context dependent, right? If that line was placed or rectangle was placed close to another thing drawn or not, it would maybe change my answer. So have there been tests or studies placing it in different contexts to evaluate people's response and see how that?
So you're totally correct that the overall context matters. We are working now on kind of an extension of that work that I mentioned, where we are trying to account for context. Yes, it's a threshold is simplistic. I mean, again, it works on a lot of data because there's certain kind of, let's say, when it comes to parallelism, we know that study I cited from 99, which says roughly 20 degrees is where people stop seeing things as parallel. Well, in reality, what it kind of means is at 30 degrees, they're definitely not parallel. At 10 degrees, by God, they are parallel. Whether it's 21 or 19, So yes, those thresholds are never hard. There's always kind of a fuzzy area, and that's where context will matter. So you want exactly like humans can see the whole context. I mean, that's kind of the big advantage of humans over algorithms, right? We see an entire drawing. We just process everything in our head like that, right? Algorithmically, you usually kind of try to break your data into small localized pieces. And then, of course, you kind of end up needing some kind of thresholds, but yeah, there's definitely a very fuzzy areas there.
Got it. Great. Okay, thank you. Okay, if there's no further questions, I'd like to thank Dr. Sheffer for the really great keynote talk, and we can kind of close the keynote session and get ready for the next set of talks coming up in a bit.